Okay. So I'm Simon O'Toole from Macquarie University, Australian Astronomical Optics, also known as just the AAO. So that's how I usually refer it as. I'm going to be talking about some of the work that we're doing in the Data Central project. It would be remiss of me to not mention our funding agencies. We are funded through public money through the NCRIS scheme there you see on the far left. That's the National Competitive Research Infrastructure Scheme, which is part of the Department of Education, for the Australian government. And that money is distributed by Astronomy Australia Limited, which is sort of an overarching body in astronomy across Australia that distributes money for all sorts of different projects, ranging from ours to the Square Kilometre Array project, to some of that money, and access to supercomputers at NCI, which is also listed there. That's the National Computing Infrastructure. That is a system based out of ANU, Australian National University, that hosts one of the largest supercomputers, or the largest current supercomputer in the country, and a lot of support for researchers and academics around Australia. We also do collaborate with the Australian National University more broadly in this space. And I just thought I'd highlight this beautiful picture taken by Michael Goh in Western Australia of the Milky Way galaxy that you see there. The sort of the band that's hooking across the sky over the pinnacles in Western Australia. So that is the romantic side of astronomy. The real side is a lot more data intensive. So who am I and what is Data Central? So I'm a former research astronomer, as was mentioned. I have a PhD in astrophysics, but about almost 9 years ago, I switched in to become more of a data engineer and manager, and have been at the AAO. I started there as a research astronomer and then moved across. The AAO used to be part of the Australian government, the Department of Industry, Innovation and Science. It's had multiple names, but that's what it was when we left. It's now the Department of Industry, Science, and Energy and Resources. But in 2018, we moved over to become part of Macquarie as part of sort of a funding rearrangement. So Data Central is the e-research platform that we've been building for the past 6 years. And it's developed to help researchers manage their data, publish it, and share, as well as analyze it. We aim to support the full data lifecycle, and primarily we work in astronomical data. So that means from the time the data comes off the telescope, which is what I'll be talking about today. But we're also moving into other areas of research. So that might include laboratories or other field work, and then take that through, support the teams that are working on the data, all the way through to their journal articles, which are published, peer-reviewed science works, and then onto the data archives, so that data is shared across all researchers. In astronomy, this is a big thing. It's basically how astronomy is done. You take your data and share it. But in other research areas, data may be proprietary or sort of kept close to people's chests for a little bit longer, and only published data is made available. So the background and motivation to astronomical data. So astronomy data is classic. You can consider it as classic big data. We have the 5 Vs, although when I started in all of this, it was the 3 Vs. But we're really moving into the 5 Vs now. We have a volume, so the Anglo Australian telescope, the AAT. Over the last 47 years, it's collected about 15 terabytes of data. The data rates early on were very, very small. We basically, if you can imagine your digital camera having only 1 pixel, that's what the data coming off some of the detectors was like in the early years. but now we have many megapixels. So we're typically anywhere between 8 and 16 megapixels per image that's taken now. So that 15 terabytes, the first 30 years or so was approximately 1 terabyte, and then it's been increasing. The data rate has been increasing from the AAT for the last, say, few years, maybe 5 years. We've really probably had at least 10 of those 15 terabytes in that time. However, the AAT is nothing compared to radio telescopes, and then so current and future. The 40 petabytes is 8 years of the Murchison Wide Field Array, which is a radio telescope, which is leading up to the big one, the Square Kilometre Array. So 40 petabytes is actually not the amount of data they've taken. That's the quota that they have at the Pawsey Supercomputing Centre, and 40 petabytes rather of data is what they're able to host there. But then in the next sort of decade or so, we'll see the Square Kilometre Array, and in 1 year, the Square Kilometre Array will collect around 600 petabytes of data. So that's when we really hit the exabyte regime, and we start talking about exascale science. Velocity. So obviously you can imagine that at the AAT, where we are only collecting terabytes of data or storing terabytes of data, maybe 1 or 2 per year, we're taking not very much data per night, no more than around about 15 gigabytes per night at the AAT. However, when we come to the Square Kilometre Array, the SKA, will be more in the regime of 1 terabyte per second. And that's how we get to our 600 petabytes per year. And the data rates are so large that we won't be able to store all of that data. So it has to be reduced and processed basically at the telescope before it can even be moved down to the big data arrays, which will be hosted in Perth. We also have a large variety of data, and the raw data here is, in many cases, it's really an image, but it's an image of a spectrum. So that's sort of, you can imagine the rainbow fingerprints of distant stars and galaxies. And then when you come to radio telescopes, they're often they can be a single pixel style data flow, similar to the early years of optical data, so data with mirrors, but also now large arrays of voltages and something called visibilities, which is a complex term that I don't even understand myself because I was never really a radio astronomer. And then the veracity, the fourth V, understanding and removing instrumental effects. If you consider when you take a photo with your phone, if you take it at very low light levels, so in dim light in the evening, for example, you end up seeing sort of like this grainy kind of noise pattern, particularly in the darker patches of your image, and that is the kind of effect that we need to remove, because that is hiding some of the very, very faint things. That the things that we're looking at here are very, very faint. You can't see them with your naked eye. You need very large mirrors and very large radio dishes, often many or tens or even hundreds of radio dishes to measure these objects out in the distant universe. And then the value, of course, of this data is just expanding human knowledge. You can take it at the high level, but also obviously these facilities all cost a lot of money to set up and to maintain. So the cost per observation, you can also consider each observation and the data with it has a value, an actual cost value. So for the purposes of this talk, astrophysics can be divided into 2 parts. So you have time critical science. So that's basically things that go bang, which is the top little animation there, and then everything else. So there may not be a bang, but you may still need to have timely data. So something you may need to look at something and how it changes over time, over many days or years, or it may not really change at all. But you may want to still try and get as much data in a reasonable amount of time as you can. So here, as I said, we're focusing on the time critical for the sort of the main use case of this of my presentation here. But everything else is no less important. It's just a different kind of observation and different data and a different sort of science case. So I will probably use the term use case and science case interchangeably throughout this presentation. So what we're really talking about here are things that go bang. So they can be explosions, collisions, and mergers of things out there in the wide universe. And two of the key use cases are the merger of black holes and neutron stars. And black holes are things that you might get at the center of large galaxies, including our own Milky Way. There's a very large black hole, which is 1,000,000 times heavier than our own sun. And in some galaxies, they're even larger than that. They may be 100 million times larger than our own sun. And neutron stars are things that are basically at the end of a star's life. They'll either fade away, peter out, and fade away, run out of fuel, basically, or they'll be so large that they explode in a supernova, and those supernova explosions will either lead to a black hole or a neutron star, which is not as densely packed as a black hole. You don't have the same gravity. I mean, you'll probably have heard that black holes, nothing can escape a black hole, even light. A neutron star is not quite like that, but it is very, very dense. And so it's called a neutron star because all of the other parts of the atom, the electrons and neutrons, protons rather, all get squished together and become neutrons. And they form a very strange material indeed. And because of these collisions and explosions, etc., you need almost immediate observations. You need to know, if you want to understand what's going on, ideally you would capture the information before the explosion, and in some cases that's been done, but certainly as soon as possible afterwards. And then you might want to observe these objects for a few days or weeks or months after the actual event has taken place. And then the data processing must also happen rapidly. You need to in order to understand the phenomenon, what it actually is that's happened, because oftentimes you don't have that information until you look at it afterwards. You want to be able to find out what it is very quickly to see if any follow-up is required, because there are some things that go bang out there that aren't quite as interesting, a little bit more commonplace. Especially within our galaxy, there are things called novae, so not super. And so they're stars that basically get very, very bright for a short period of time, but then they fade away and then they stay as regular stars. There's no massive explosion in quite the same way. And these research fields are very, very competitive. To understand what's going on here, you can get, it can be very, very prestigious, and you can end up on, front cover of major magazines like Time, the front page of major international newspapers. For example, the New York Times is often something that people aspire to, as well as being able to publish their results in highly prestigious research journals. So in order to talk about astronomical data, we have to start talking about astronomical data formats. So observational astronomy and radio astronomy to some, or observational optical astronomy, which is mainly what I'll be talking about here, but radio astronomy also uses something called the Flexible Image Transport System format, or FITS. FITS is quite an old format. It's been around for over 30 years. It's quite standardized, although as you probably know, with most standards, it's all about the interpretation. And it's maintained by NASA, the Goddard Space Flight Center, and also in collaboration with the International Astronomical Union, which is the body that represents all astronomers throughout the world in every country. So it's a pretty simple format, FITS format. It consists of an ASCII text header, which is seen here on the right, and that comes in basically its key value pairs, or maybe you could. It's really a it's a triple, not a tuple. It's a key, a value, and then maybe a comment as well, and that provides its own sort of challenges. And then you have your text header. So every FITS file has a text header, and there are a standard set of keywords or keys that are used. In the picture on the right there, you see the top sort of 16 or so are some of the standards. Some of them towards the bottom are standards, but some of them are very particular to the telescope or the instrument that was being used. And so that you can also, in a FITS file, you can not only have just your text header and binary image, which is the observation, but you might have multiple images and even multiple headers. So there'll be an extension. And so you have a primary image and header, and then extensions associated with it. And that may contain other information. It may contain variants or other information that was acquired during the observation, or it might be something that is done as part of the post-processing of the image. The extensions can be images, but they can also be binary tables. So basically, just a binary form of a table, not anything particularly fancy. And we do use other formats in astronomy. CSV files are remarkably common, particularly for transport, and HDF5, which is, I think, more of a research format. So you may not have come across that one. It's a hierarchical data format, and they're up to the 5th version of it. That's something that was implemented by geoscientists and atmospheric scientists, and that's often used to transport data around those two formats. And then we have started seeing a increasing uptake in something that you're probably more familiar with, the Parquet format, and that's used for storage. So data acquisition. So you have your telescope, whether it's a mirror like the Anglo Australian telescope, the AAT, or radio telescopes like the SKA will be. There is also one at Parkes, very famously, the Dish in central New South Wales, that was involved in the moon landing, but it is still taking science data to this very day. So you take there are two components to observations. In order to observe these beautiful images here of a galaxy and a cluster of stars in a gas nebula, you need science frames. So that's where you actually point at the object that you're interested in, and then you need calibrations. And this is what I was talking before about with detector variations. You have variations which are sort of like a base noise level, and then variations that are really how the detector responds to light across the detector. So different pixels will respond differently, and often that happens in some kind of smoothly varying way. And so we want to remove that when we're talking about images. And then we also need, when we're talking about spectra, so the rainbow fingerprints I mentioned earlier, we also want to get the wavelength, the actual color information there. That's not something that comes, you need to sort of do a calibration and have some known wavelength source that you compare your observation to. And it passes through the same instrumentation, through the same hardware. So the observations are made using a coordinate system. It's similar in some ways to, to latitude and longitude on Earth. And in fact, there is something known as galactic latitude and galactic longitude, but the reference system is different. Primarily, or in many cases, we'll use coordinates called right ascension and declination, and that's sort of related to azimuth and altitude, if you're familiar with sort of some of the naval terms, and it's defined using something called the World Coordinate Systems conventions, and these define how we map the celestial coordinates on the sky and then map them onto a detector, and all of the metadata around that, how what the reference points are, go into the FITS header, and so they can be read, and there are lots of libraries that you can use, Python in particular, but also R and C and other languages can read FITS headers and extract this information. So the problem that we have, though, so I've given you the background of what the data format is and everything, is that telescopes need to be in remote locations. For a radio telescope, it needs to be radio quiet, so you can't have mobile phones everywhere, smartphones. You can't have microwaves even. There's a famous story of an astronomical event that wasn't, because it turned out that someone had been running the microwave in the visitor lodge of the telescope that was being used. And so for several years, so all of these papers and even conferences about these strange events that kept occurring, and why were they only seen here? And it turned out it was actually microwave. So we can't have that information. You will see buildings are either very heavily shielded or there are no microwaves at radio telescope sites. And also, particularly for optical telescopes, it needs to be very, very dark. No artificial lighting. We should have no artificial lighting. So the problem is that data centers can't be that isolated. Peter mentioned, I think it was on Monday, that we have this problem that you need to be very far away from built-up areas in big cities. So central New South Wales, just outside of Coonabarabran, is where the AAT is, and the SKA will be primarily in remote Western Australia. So we need an efficient transport mechanism to move data these many hundreds of kilometres. So the case study for this talk is the Anglo Australian telescope. The data there is typically, you might have multiple cameras, and they're 32 megabytes per observation, with multiple observations up to 4. So therefore 128 megabytes per observation of data. The telescope that you see here, this is a slightly old image, but it does pretty much still look like this. There's a bit of extra safety gear on it these days. There are 2 instrument control computers, depending on what instrument is being used, and that would sit at the very base of the telescope, or perhaps even in a room off to the side. And then you have a fiber optic cable or mirrors to direct the light into those rooms. And the control computers that control the instrument control the cameras as well. There is limited compute and storage capability on the mountain, and that's in part because it is just isolated, but also for a long time there wasn't much needed. The data sizes weren't large, and so there isn't really the capacity to host a large amount of compute on the mountain. And these days, not as many astronomers actually go to the telescope. Mostly now it's remotely operated from their home university. They're even starting to move to a model where in certain situations you may be able to run it from your home, but the control computer has a 4-headed monitor, so it's still primarily done at a university site. In the case of transient astronomy, so that's where I'm talking about the things that go bang, things that come and go very rapidly. Astronomers don't even go anymore. Someone else at the telescope will take the data for them. There is a small crew of staff who are always at the telescope to drive it. Basically, this thing weighs many hundreds of tons, and so you can't just have any old person come and use it. You need an experienced operator to run this telescope. So the problem is we need to move the data away from this remote site and process it rapidly. And this is research and university, so we actually have a very limited budget for this. So Siding Spring Observatory, it's 470 kilometres from Sydney and around about 650 kilometres from Canberra. There is a 10 gigabit pipe that comes from Siding Spring Observatory, which is where the telescope is, to the main trunk, which is Australian Academic Research Network, which is also known as AARNet. There's the pipe from the observatory connects to the main trunk at Coonabarabran, and then comes down to Sydney and Canberra to NCI and the AAO, following various paths. So our solution, so we're using a system called Apache Nifi, which I'll talk about in a little bit, to move the data from the telescope to the AAO, which is just in North Ryde in Sydney, and to NCI, which is, as I said, part of ANU on the main campus of ANU. Then we've passed the FITS header using a Python script, and then place all of that metadata that we extract into a MongoDB, and put the files themselves on a file system. And then we have a system that allows astronomers to come and query the data and retrieve it as they need, and that's a system built using just React and Python with the Django framework. And then we authenticate, because we do need to have some kind of access control, particularly for, I think, astronomers for the AAT get 18 months where no one else can access the data. They have to apply to access the data, and then go and observe it. They have to put in a sort of a science case, and that gets reviewed by a panel. And so they have 18 months from the moment they take the data to the moment it becomes public to the world. And then we do data processing using a combination of Docker and bespoke software, and this allows us to improve the performance of what you'll see is quite old software. So here's the technology solution. So we have Nifi, MongoDB, CAS, and then React and Django plus Docker and the bespoke software I mentioned. So Nifi, if you're not familiar with it, this is from the Nifi website. It's an easy to use, powerful and reliable system to process and distribute data. And the name comes from the original US NSA name, which was Niagara Files. It was part of the 2014 NSA technology transfer, and it's a extract, transform, load system that was open sourced as part of that system, and much of the software development is now done by Cloudera for Nifi, but it is an Apache project, so it is open source and open to the world to contribute. So it understands many different data formats, many of the data formats that we've heard about already at this conference, Parquet and Kafka. It can understand some of the streams from Kafka, and many different storage systems, and it can handle these natively. So it can be obviously file systems, but also S3 like object stores as well. And so Nifi, it can be run as a single machine, which is at the moment what we do, but it can also be managed through a cluster using Apache Zookeeper. And then you can also have a server-to-server connection, or a client-to-server connection using a sort of a subset of Nifi, which is called Minifi. And that is the latter is what we use. So we have a Minifi client sitting up at the telescope, and then a Nifi server down at both Canberra and in Sydney. So it manages workflows using a GUI, which is similar to the one here, and you can kind of see the different boxes represent different processing steps in the workflow, and they are all connected, and so you can have branching. You can have them basically as complicated or as simple as you need them to be. And so we have things that basically data arrives and then just is written to disk, and then there's also processing steps where the data has some kind of parsing, as I mentioned before, and then might get written to a database, and then you can send an email and do all of those sorts of communications with users to let you know if things are going well or not so well. So you can move database entries as well as files, so you can have it monitor your, for example, a MongoDB. We're in a separate project. That's what we do. We actually look at a database directly and then copy collections down as required to our North Ryde site. So MongoDB, you're all very familiar with that, I'm sure. We're using a community edition because, as I said, researchers are poor, and we use it on premise. We don't use the cloud instance, mainly because we have data volumes that can get quite large. Each observation's metadata is considered as a document, and then we have a nested structure. So the FITS header that I mentioned goes in as a subdocument, and then we also have an interoperability component, so a standard way that other data centers also implement, and that goes in as another subdocument, so that people can come along and do one standard query to our data center and then to other data centers and expect to get data in the same basic format, get the results in the same format. So because I mentioned the WCS earlier, we really would like to use some of the features that MongoDB has for geospatial work. However, the WCS is far more complex. The reference system is far more complex than S2, which is what the MongoDB geospatial system is built on. And we have for some time been considering a project to add something called WCSlib as an offshore coordinate system to MongoDB, but it's a fair bit of work, and we don't have the resourcing and funding to do it as yet. But it is something that would be really cool because it would allow us to use to do a lot of the database queries, to basically say, what data have you got at this point inside some radius on the sky, and so it's spherical geometry is what we're talking about here. So the Central Authentication Service, or also known as CAS, it's managed by a software foundation called Apereo. It allows the use of multiple authentication protocols through one system. So CAS has its own protocol, but then OAuth and SAML, and you can delegate to other systems as well. It can handle multi-factor authentication. It integrates with all the big services, and it's hugely customizable, but it does work well with sort of quite minimal configuration. So you can do some quite powerful things with basic configuration in it, and it can hook in obviously with things like LDAP as well, which is how we use it. Ours connects to an Active Directory data store. So the web technologies, basically what we are trying to do is handle the queries from astronomers, for anything that's publicly available. They come along and say, I'm interested in this object at this position in the sky, or maybe data that was taken on a particular night, and then then we do authentication with CAS and also between the React and Django systems with just JSON web tokens. And as I mentioned, the data can be proprietary. So data reduction is really the processing step. That's where we take these quite large images and literally reduce them to a smaller scale. We're using Celery inside a Docker container, and this system spawns new containers using DockerPy. We chose that as an orchestration system because it was easier to get going for us than something like Kubernetes, where, as I said, we're doing all of this on premise. The containers run legacy software, which is known as 2D FDR, which means 2-degree field. That's the size of the field of view of the telescope, which is quite a large patch of sky. It's half a degree across is the moon, so 2 degrees is the full moon rather is, so 2 degrees is very large, and data reduction, 2-degree field data reduction, and it's legacy software, so it's written in Fortran 95, and this is causing us problems. This is one of the reasons to containerize it, because if astronomers want to run this, it's getting harder to compile. It's still possible, but astronomers mainly use Macs, and so that's quite a difficult thing to support all the different versions of Macs and their the different ways of handling some of these libraries. And by using containers, we can parallelize this data. So we're processing just on a single dual CPU server, 120 gigabytes of data in around about 45 minutes. Now, if you had a large cluster with multiple nodes, then you would probably be able to do this even faster. But this is an improvement over what most astronomers do, which is use their laptop. And so this is something that we're just implementing at the moment, but it's going to go live into production in the coming months. So this is actually the data. This is what you get. On the left is the raw data image. It really is a 2000 by 4000 pixel image, and the sort of the various lines, the curved lines that you see there, primarily, in fact, are due to the atmosphere. They cause some of those curved lines going from left to right, and going from top to bottom are the individual spectra. So the observations are taken using a robot that can observe 400 objects at once and gets a spectrum and passes it through the spectrograph. Basically, as I said, the rainbow fingerprints, and then you end up on the left. This is just a single sort of slice from the top to bottom of the raw spectrum. This is the reduced spectrum. So as you can see, it's a lot smaller. It's been calibrated for wavelength. So for those of you not familiar with wavelength scales, you can run from 4,000 angstroms there, that's blue, very, very blue light. Still, you can see it with your eyes, and right out to 8,600 angstroms, which is just beyond the capability of your eyes, into the realm of cat vision. So what we have here, that just to give you a little bit of context of what we're trying to do here, is understand for these things that go bang, how far away they are, what the galaxy that they're in, because we haven't had a supernova in our galaxy for hundreds of years. How far away they are, and that gives us an idea of when this might have occurred, and then some of the properties of the galaxy that the supernova is in, and then in many cases you'll try and work out properties of the star that exploded, or the objects that merged to create to form the black hole. So this is what we're trying to do. And so this number here is the Z is known as the redshift, and it's basically it's sort of related to the galaxies as they're moving away from us. The universe, as you may know, is expanding, and so redshift you can consider as a proxy for distance. So how far away the object is. The higher the redshift, it can go up to I think the highest recorded redshift is around about 8 or so, 8 or 9, something like that, and that's also therefore very, very far away. But because of the speed of light, it's a proxy for time as well. So if the higher the redshift, the longer ago the event happened, and also then the closer to the beginning of the universe that the event happened. So some future challenges. We're working with the European Southern Observatory, their very large telescope, and eventually their extremely large telescope. Astronomers don't have very good imaginations when it comes to naming things, but the very large telescope is what you see in the image in the background. You can see the top at the top there. That is sort of the top of the telescope, and the mirror itself. This is an 8-meter mirror at the very large telescope. Is at the bottom, and the huge mess of the spaghetti mess of cables and tubes. There is an instrument where you have called MUSE. I can't remember what that stands for. It's another terrible astronomical acronym. But there are 24 16 megapixel cameras, so that's 4,000 by 4,000 on a square, and they have continuous flow cooling. So that's what some of those tubes are. So they're cooled with liquid nitrogen down to minus 100 and minus 80 degrees, something like that. And this means that the background noise is very, very reduced, very low. So it gives you around about 1.5 gigabytes per exposure, and every science frame that is acquired needs multiple calibrations because for the sensitivity that people are trying to reach here, you need to really make sure you get rid of all of that background noise, that bias, sort of staticky kind of granular noise that I was talking about before. And then the challenge is to move the data off Cerro Paranal, which is in the north of Chile, in the middle of the Atacama Desert, down to Santiago, and then to Munich, which is where the European Southern Observatory's main headquarters is, and also to Sydney. And we have a project where we're trying to do that. And then the data reduction itself requires quite a lot of memory, 256 gigabytes at least, and many cores in order to process this large volume of data. So that's something that we're working on right now. It's coming to a head where we need to really improve some of the workflows there. Then beyond that, in the next few years, next 2 or 3 years, is the Vera Rubin Observatory that will come along in a slightly different place in the Atacama Desert in Chile. Chile is a very dry place. In many places in the Atacama Desert, they have never recorded rainfall in 400 years. So Cerro Pachon is the location for the Vera Rubin Observatory. It's also an 8-meter telescope, but it has a very, very large field of view. So it's able to observe the whole southern sky every 3 nights in 6 colors, sort of filters. And it's also liquid nitrogen cooled, but it's a 3.2 gigapixel camera. So it's acquiring 30 terabytes per night. And it will conduct a 10-year survey. So the data reduction on the fly is once again required for transient phenomena. So this is one of the challenges. Most of the data reduction will probably take place in the United States at the NCSA, the National Computing, and I can't even remember what that stands for, but it's the big supercomputing facility in the US, the government funded one. So it's a 10-year survey, and we'll have, once again, we're just hitting the exabyte scale. And this is process data, half an exabyte of process data. So the raw data will be even larger. So that's what happens when you observe the whole southern sky every 3 nights in 6 colors. So there's a dedicated fiber from Chile to the US, and that was with the help, piggybacked, I think, on a Google Fiber run there. So this project is partially funded by the Department of Energy in the United States. So that's where they got some of the funding and help with Google there. And a subset of this data will come to Australia. We're still in the process of working it out, but this project will probably start next year. And then beyond that, towards the end of this decade and into the next, we have the Square Kilometre Array. So there's actually 2 sites. One is in South Africa, and one is in Murchison Shire in Western Australia. You can see it there on the map. The population density is very, very low, so it's very, very radio quiet. It's also very dark, but that's for radio telescopes. That's not so important. So they have an 800-kilometre fibre, which takes the data from the current sort of Pathfinder telescopes. There's the Murchison Wide Field Array that I mentioned, and something called the Australian SKA Pathfinder, or ASCAP. They're both at the Murchison site at the moment, and they currently have a 200 gigabit per second fiber connection from Murchison down to Pawsey Supercomputer Centre in Perth. And so for now, I don't think they're doing the data processing on site, but when they build the full SKA, they will need to do the processing in situ and in Perth. And in fact, I think there's probably going to be a dedicated supercomputing centre that sits alongside Pawsey. Pawsey is a national facility, so it's used by researchers in all sorts of different fields and disciplines. So thank you very much. You can follow me on Twitter at Dr. Simo. And of course, this work is not the work of mine alone. There's large contributions from the people here listed below. So thank you very much.